So the next topic is about serial interfaces. There are several kind of serial interfaces. For example, there are some devices. I actually had some material somewhere. Sorry, I haven't included those here. I try to find them. But anyways, fundamentally there are different standard serial interfaces used with the microcontrollers. The most common ones are this traditional universal asynchronous receive transmit kind of the transmission. So it's 8 bits and usually it's a one line out and one line in. And then there are these the synchronized ones. Most common ones are I2C, SPI, and Onewire. Yes, Onewire. That's also synchronized communication. Although there's the difference between synchronized and async, the signal is basically that on synchronized there's also a clock signal. Onewire does not have clock, but it's still considered synchronized, I think. Okay, but anyways, it looks like it wouldn't be, but but anyways, so this normal UART, well, normal, old-fashioned UART kind of the transmission, which was first used, for example, on mainframe computers and to hook up the terminals to the line. Maybe I should write something on the table. Okay, something. There we go. I'll turn off that for a while. So about this what kind of the serial the transmission. Basically, this is a device that can be used for example, RS-232 communication line. But this is actually a standard, which defines also the voltage lines and that kind of stuff. And this standard was defined for hooking terminals to a computer or mainframe. And basically hook up a terminal or mainframe to modem, and that would go to the telephone line and hooked into the other computer on another terminal. So ask your grandfather what this modem looks like. On the other hand, if you are subscribing any data subscription like DSLs, that's actually a modem right there. So it just translates this serial line data so that it actually travels well on those telephone lines. Anyways, that one is a simple protocol which has some parameters like speed or bit rate. Yeah, not speed, but bit rate. And only specific bit rates are available or can be used. Most common are 9,600 and 19,200 bits per second. But there are also, 2400 and such kind of things. There are several ones, but these are basically coming from the history. I was really happy when we, on university where I was studying, we had first the bit rate and 150 bits per second between terminal and the mainframe. And then they doubled it to 300. Then you could actually type so that you can see what, all the characters. You need to wait. Okay, so bit rate, then number of bits. Number of bits. Okay, number. Number of bits. Usually 8, but it can be also smaller than that. 8 or 7, depending, but that's most common. Down to 4, actually. Less than 4, it's not allowed. Then parity. No parity is the most common, even parity or odd parity. Nowadays, usually the data integrity is tested by some better means than just one single bit. For example, cyclic redundancy checks, CRC numbers. And the fourth one here is actually the number of stop bits, either 1 or 1.5. And this actually, how to make 1.5 bits? Well, this is actually the just a pause. How long pause you can have to have in between two the transmissions. But, one is just enough most of the time. Okay, so that's the RS-232, or without that buffering, there is a UART inside, which has the line buffering for output and input. Okay. Anyways, that UART has 2 channels. One is for transmitting and one is for receiving. And if you have any other similar DTE, data terminal equipment, another DTE equipment here, it also have the TX and RX. So, well, you just need to cross the lines, which you will need to do on our today's exercise. This one here actually is the PSoC 5 development board, but it also is a but it also has the serial to USB device inside of it. So you can use this one for debugging even with lower voltages than 5 volts. So you can run 3 volt system and use this one for transmission between computer and your device. So in this device, basically, you have those pins 12.6 and 12.7, which are marked on the other side. What you need to hook up between those, and common ground. GND. And then you have a data transmission lines ready. You just need to fix the this communication parameters, bit rate, bits parity so that they match. Okay. How do you know the parameters here? Since this is, you know, it's kind of debugging device. Well, when you plug that one into PC, then you go into PC and take the, let's see, it's the device manager. You can actually then see the ports, and on ports you will find COM port. It looks like a virtual serial port there. If you have a ancient computer with real real RS-232, then that the development board actually has also the that one, but it not anymore, not in laptops anymore, not even in my laptop. Okay, so yeah, it's really ancient technology. Yeah. So basically, when you plug this one in, it will show up as a COM port and make a note of which COM port. Since you can then take the, say, some terminal program. In Metropolia, we are using PUTTY terminals, a standard terminal, and then basically there on this one you see the parameters, which you then put on your terminal, and then you can actually do the use your terminal program to communicate with your device. And okay, these parameters, of course, these must match your PSoC program. Okay, a bit complicated, but that's how you get it, the serial line run. Another serial line what we have today is the was it Onewire? Let me take a quick look at the yes, DS18B22, or actually we had DS1820 devices to as a Onewire Onewire temperature sensors. Take a closer look, since this looks quite the same as the device I gave you earlier. It's the same package. So make some notes on which one is which. Or, well, you have young eyes, so you can always, you know, just read them. I personally will use this one as a magnifier. Okay, so there we have the Onewire. It's a was it Philips or some? No, it's not Philips. Was it on Dallas has the yeah, Dallas has the IPRs for the for the Onewire. But the name Onewire actually comes from the fact that it uses two wires. Okay, here we have the master device, which is powered normally. Then it has actually this Onewire line going to the device. The Onewire means that you can actually power it up also from this line directly. You do not need necessarily to power this one from any external power supply. But since that is available, why not to use it? Okay, in addition to that, I think you also need a pull-up register here. But anyways, the device here is designed so that actually it has also system to take some of the power to the small capacitor inside of the device. So the device functions without any external power too. And that another wire is this ground connection. But well, signal is in one wire. Good. It has its own protocol, which is not straightforward. And basically you need to read the that data sheet quite carefully, since you need to actually initialize it and set the internal register so you can read the data. But on that data sheet, there are instructions how to do it. I have the data sheet for that 18 plus 22, or 18B 22 plus, which is code compatible. But since we have that 1820, I would recommend finding the data sheet for that one. There is not much difference, but the 22 is a little bit enhanced version. Okay, so one wire sensor. So today, basically, you will start from the this earlier exercise. We had this sampler on sampling rate of 2 samples per second, and make that sampler actually also to sample the this one wire sensor. So you will go when earlier you just calculated the temperature from the analog sensor. Now you also go and read the value from this digital one wire sensor. And then basically earlier you would put the output only to LCD. Now you would be sending the data also to the serial port. Okay. You also need to, well, that will be the first part. Try to just add the one wire sensor in addition to this analog sensor and plot both of those here. Then modify so that you can actually have the serial port output. And when you have those, then you can actually finish the exercise by doing it a kind of intelligent sampling circuit. So it also reads. Basically, your system would wait for the command. So there's the last one on the task. They modify the code such that the system waits for a command from PC and does the following. Well, so basically you type here A, your device should reply by this identification string. Simple. And that should show up on your terminal. Okay? And S means that it returns one sampler from ADC, actually ADC and one wire. Okay, I need to modify that a little. Where's my exercise 4? Now, analog and temperature sensor. There, single value. And then C means sample and return data continuously, and X is stop sampling. Simple kind of the interface. So after that, you have a data logger. Haha. A lot of wires. It looks like a mess, but anyways. So that's the stuff for today's exercise. Today we won't have much of challenge yet on fitting all of that stuff inside of the PSoC, but tomorrow we will have. Where's my, okay, there it is. There we go. So that's the, wait a minute. That's today's exercise. So we have Onewire sensor and the analog sensor, and then basically send that one to LCD and USB serial port. Let me change that a little bit. So. So that analog sensor we already have. We just add there Onewire sensor. Should I actually change that one a little bit? So that we have LCD part we have. There. Better. So analog sensor LCD we have, and the sampler inside. So basically what we could do now is to just clone the project, but it's not 2B, it's actually I think it's 3, exercise 3. You know, it's too easy to leave those errors here since I can change them as I speak. Okay. Anyhow, let's take a quick look on, or a better look, what we should be doing today. So this is the exercise 3 project. First thing first, so make sure first that it works. So sample two samples per second, and give us values that are something above 25, since my sensor gives 27. You have something like 26. Yeah. Okay, and that's my code. C. Process, display, and COM. That COM is already there, so I encapsulated those in on different files. Yes. So basically, how to encapsulate the code, I created 2 files. So one is process.h, that where I put the code, and also then the process.c, which basically is just the prototypes for the functions. So process.h is simply these 3 prototypes, and that's it. And process.c has those functions: process, display, and then communicate. So that's one way of doing stuff. Yes, exactly. So if I have on main.c, I have this, let's see, main.c. Main.c, I have these the global variables. I use only these 2 global variables on my process. since I don't need the times up, since I know I go there only when times up. Okay, and on process, to read those correctly, you declare those as external without the initial value. Otherwise, that's a syntax error. Okay, so that's the real variable, and this is just telling to the linker where that variable is found. So it's externally. It's not inside of this scope of this file either only. Okay. So chip level. We need yes, exactly. I was about to do it, but all right, new project. PSoC exercise 4. Actually, I already have one of those, so I'll just put version B. I tried it first. Clone existing and exercise 3, and that CMX file is the project description file. And then we'll wait, and it blinks, 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 and now it's exactly the same. It's a good idea to actually build it. Build it and program to make sure that nothing changed during our cloning process. For example, you could have accidentally clicked the different processor there. Or not that accidentally. If you find out that, okay, this device does not have enough of resources, you could go to a bigger device. Okay, so I have this 16-bit timer, and that one, and it seems that it still works. And I have all those code also here. That's nice. Okay, and those are local copies, and more then I could actually start adding some devices here, and I need UART and yeah, Onewire. Yes, I'll show you what happens. There's small hiccup, not a problem, but a hiccup here. So if I add here the UART, the UART can actually be let's see, placed to, well, it seems that it can be placed only to this location, right? No, it actually can. Oh, no, yeah, that's the only place we can put it.